this lesson, we will discuss training Bayesian belief networks. We will start with reviewing Bayesian belief networks, then move to training the networks, where we will focus on two scenarios. When the network structure is known and the variables are either observable or hidden. After that, we will touch on the plate notation for representing complex networks. Let's revisit the structure of a Bayesian belief network, which is represented as a directed acyclic graph, where the nodes are the variables and edges indicates conditional probabilities and captures the dependencies between the variables. For example, in this graph, B is independent, A depends on B, and C depends on both A and B. To compute the probability of an event, we use the chain rule to express the joint probability. For example, we start with B. Since it has no dependencies, we get a prior probability. Then we condition on A given B, and finally we condition on C given both A and B. In general, when training a Bayesian belief network, there are four possible scenarios. On the network structure side, the network can be either known or unknown. So, in other words, do we know how the nodes and edges are laid out? Do we know how conditional dependency is presented in the graph? For the variables side, variables can be either observable, we can directly measure them, maybe through an experiment, or variables can be hidden. We have no information, we need to make inferences from the data set. So an example of a hidden variable, let's think about the fire alarm example. Suppose there were no cameras installed inside the buildings. We don't have any information about the tampering events. So in this case, this becomes a hidden variable. For training Bayesian belief networks, the most straightforward scenario is when we know the network structure, the variables, and we have a mechanism to construct the conditional probability tables. Then all what we need to do is to translate the probability question into a mathematical expression. Sometimes we can answer it directly using factorization and probability table. Other times we might need to apply marginalization or recognize a pattern that resembles a Bayes rule and then substitute and go from there. In the second scenario, the structure is known, but some variables are hidden. For example, if the graph suggests a tampering variable with associated probabilities and conditions, now the goal becomes to learn the value of these unknown parameters using the training data. We can always use the structure to define the optimization task. Also, we can start with some initial assumptions about the probabilities, then refine them as we go through the learning process. To summarize, in order to estimate the unknown values, we can start by assigning those random probabilities and then optimize the likelihood based on those initial assumptions and the training data. Eventually, this becomes an iterative process where we use methods like gradient ascent to gradually move towards the best solution. One common algorithm for this process is called Expectation-Maximization, or EM, which helps with optimizing parameters when we're dealing with hidden variables. To get a sense of how learning by computing a gradient works, let's say that we are going to assign random values for lung cancer, family history, and smoker, and construct the probability condition. Probability of lung cancer equals yes, given history equals yes, and smoker equals yes. Given D training examples, we will choose the parameters that maximize the probability. And since there are D examples in the dataset, we multiply them by the unknown probabilities and solve the resulting problem, which is an optimization problem. So to solve the optimization problem, the goal is to maximize the overall probability. We take the derivative of the log of the probability because taking the log is going to convert the product into a summation. As we all know, this simplification allows treating one variable at a time while keeping other constant, which makes differentiation process easier. So if this approach works, it's going to be great because we will have estimates for these unknown values. But if the direct solution doesn't work, we will have to apply gradient ascent since we are maximizing. In some case, the optimization might result in weights greater than 1. That's why we have to normalize between 0 and 1 because these values represent probabilities. There are 2 more scenarios left when the network structure is unknown and all variables are observable, and when the structure is unknown and the variables are also hidden. Since this goes beyond the scope of this class, we provide a couple of references on probabilistic graphical models. Lastly, we will talk more about simplifying a graph representation. So far, we used overly simplified example like the fire alarm or the disease scenarios. But in more complex cases, we might have a vertex with so many offsprings that all belong to the same category. To make such graphs easier to understand, we use something that is called the plate notation. In plate notation, a square is used to group related vertices, and the vertices inside the square summarizes the structure. In other words, this is a cleaner representation. In this example, as you can see, all the shaded vertices represent grades for some course taken by students. However, the focus here is on 2 features: the difficulty of the course and the number of hours student worked on the homework or the exam. So it doesn't matter which course or which student it is. We know that there are many courses and students, and we are concerned about the grades given the difficulty and hours worked. So this is an example of the plate notation, which simplifies the representation of those overly complex networks. In summary, we discussed training Bayesian belief networks, and we touched a little bit on the plate notation.